Hello and welcome to Mrs. Law's class. In this video, I'm going to talk about the limit of a function. Suppose I have one whole pizza and I decide to eat half of it. I can still hear my stomach growling from hunger. So I decide to eat half of what's remaining. So that will be a quarter of the entire pizza. I'm starting to get annoyed because I'm still hungry. So I decide to eat half of what I just ate. So that would be 1/8 of the whole pizza. And so it goes on. Notice that I will never eat the whole pizza under this premise, but the more I eat, the closer I will get to having eaten the whole pizza. So we say that the limit is 1 being the whole pizza. Now limits can be used to describe how a function behaves as the independent variable x, which is the input number, approaches a certain value y, which is the output number, even if the output value does not exist. So let's take a look at an example. Consider the function f of x equals 2x minus 3. And suppose we select input number as x, closer and closer to the number 4. Now I've chosen the number 4 arbitrarily here. You'll see why in later examples. Fill in the input-output table and take note of what happens to the output numbers. All right, so 4 is in the middle of my table here. So I'm going to start on the left side. I started a little bit away, so I started at 2. So when my x value is 2, I have 2 times 2 minus 3. So that will give me 1. And I'm going to get closer. So I'm going to choose 3.6. Bit of a jump. So 2 times 3.6, and then minus 3, that's going to be 4.2. I'm going to go a little bit closer to 4, so I'm going to go 3.9. So 2 times 3.9 minus 3, and we get 4.8. So I'm going to keep doing this. So I'm getting even closer. So I can put 3.99 for x. And then my f of x value will be 4.98. So you can use a calculator to calculate this. And then let's do one more from the left side here. We're going to use x is 3.999. And then we times that by 2 minus 3, and we get 4.998. All right, let's do the same thing, but we're going to approach from the right side of 4. So let's start something a little bit bigger. So I start with 5. So 2 times 5 minus 3 is 7. And then 4.8 is a little bit closer to 4. So 2 times 4.8 minus 3 is 6.6. So similar to the left side, on the right side I'm going to get closer and closer to 4. So plug in 4.1, I get 5.2. Even closer, 4.01 is 5.02. And 4.001, very close to 4 as well, you get 5.002. So from the left and the right side, we can see that these two numbers here, it looks like it's approaching the number 5. So I'm going to write 5 here. All right, let's take a look at this graphically. So what I'm going to do is I'm going to graph f of x equals 2x minus 3 on this grid. Okay, so I am going to plot my y-intercept of -3. And then my rise and run is 2 over 1. So I'm going to go 2 up, 1 over. And I'm just going to keep plotting this until I get a lot of points. Okay, pull out my ruler. And then I'm going to draw my line. Oh, with a little bit tiny over. Okay. So you can see from the graph when x is 4, so it's going to be 1, 2, 3, 4, that's 4. My f of x value right here is actually 1, 2, 3, 4, 5. So graphically, when x is 4, f of x is also 5. Now, verbally, how we say this is, as x approaches 4, f of x approaches 5. Or we can go as x with an arrow approaches 4, f of x with an arrow approaches 5. Now, algebraically, this is not how we write this, but we use the word limit. So we abbreviate that with lim, L-I-M. So limit as x approaches 4, and we write the x with an arrow and the number 4 underneath the word lim. And then our function is 2x minus 3. So we know what the function is that we're looking at. And then this will equal 5. Now we could have evaluated at x equals 4. So we could have actually just plug in 4 in for x. Up here in our equation, 2 times 4 minus 3, we know that's 5. But this doesn't always work. And we'll look at some examples later that you can take a look at and ones for you to try as well. Let's take a look at a formal definition of a limit. Now, note the concept of a limit is central to calculus. Today, we will concentrate on an intuitive introduction to limits, so looking at it numerically and graphically only. Now, limits can be used to describe how a function behaves as the independent variable moves towards a certain value. So here's the definition. So how we read this is the limit of f of x as x approaches a equals L, some number, or it could be a variable. It means that as x, so what is this, gets very close to a, but does not equal a, then the function value gets very close to the number L. Now you can try this your turn 1 and you will find that it is not what you expect. And this is something that I would like you to try on your own before you move on. All right, note it is important to graph as well as use a table of values so that you can visually see what is happening. Because sometimes what you calculate might not necessarily be what is happening. So as an example, let's say that I ask you to find the limit of sine pi over x as x approaches 0. Now, if we graph, you will see that it looks something like this. It's a little bit crazy. And you can use Desmos to take a look at it. Now you'll see that as x approaches 0, in this middle spot in here, it has actually no limit, because it's actually difficult to even see on the graph. The y value, it actually oscillates. So that means that it switches back and forth between 1 and -1. So the existence of a limit as x approaches a doesn't always depend on how the function may or may not be defined at a. Defined meaning when you plug in the number, you actually will get another number. And sometimes you actually don't get a number at all. All right, next we're going to take a look at one-sided and two-sided limits. So we're going to use a graph and an input-output table, which is basically a table of x and y values, to find each of the limits for the function f of x equals 1 over x, if they exist. Now, actually, I'm going to do this in reverse. We're going to actually fill in the table, because the table actually will help me draw the graph. All right, so I'm going to pick some numbers. -2, -1, let's pick -0.5. And then from the other direction, let's pick 2, 1, and +0.5. All right, so when I choose -2, I plug it in. 1 divided by -2 is -0.5. Plug in x is -1, I get y is -1. X is -0.5, I get -2. So on the left side, I have a graph that looks something like this. All right, so let me fill that in. Okay, now on the right side, when x is 2, we get a half. Oops, should be down here. When x is 1, I get 1. And then when x is a half, I get 2. So we get a graph that looks like this. Now you can see graphically and from your knowledge that we can't have x is 0 because that would make it undefined. So we would say that 0, the value is undefined. Now we can also see that the limit of f of x as x approaches 0, they don't actually approach a number. One goes one direction, the other one goes the other direction. So we say that this limit does not exist. So we can abbreviate that with D and E. And same thing over here. Now, does not exist is not the same as undefined. Undefined is stating that there's no number. Here, we're saying the limit does not exist because it's not in existence, I guess. All right, now in order for a limit to exist, the limit from the right and the limit from the left must be equal, and it must exist. So there has to actually be a number that we can identify. And it cannot be infinity. So what we can do is we can use a special notation to indicate the one-sided limit, okay? So if we see limit f of x as x approaches a and there's a little plus sign, that means we're looking at the limit from the right. So in our graph, we could say this is our right side. And then as we approach 0, going towards this, we can see that our graph is going towards infinity. So we can say that the limit of f of x as x approaches a from the right, even though it does not exist, we can still write infinity. We usually save does not exist for when the two limits don't match. Okay. Now you'll see in the second one that it says x approaches a. This time it has a little tiny negative sign. So that means the limit from the left. So the left is actually this side. So as we approach 0 from the left, you will notice that the graph goes down, 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 down. So we would say that the limit of f of x as x approaches a from the left is equal to negative infinity. Now when you combine both of these together, the limit of f of x as x approaches a, since they are not the same, we say that the limit does not exist. And this leads us to the theorem. So a function f of x has a limit as x approaches a, over here, if and only if, and that's this IFF, if the right hand and the left hand limits, so you can see this part here, they have to be equal and it has to exist. In this case, it is L. So if the left hand limit and the right hand limit equal L, then the limit of f of x as x approaches a is also equal to L.